Hello, Physics 30s. In today's lesson, I'm going to talk to you about a process called electromagnetic induction. And in this lesson, we're going to describe qualitatively the effects of moving a conductor in an external magnetic field in terms of moving charges in a magnetic field. I did just want to point out that I'm also, even though I'm not required to do this from the program of studies, I am going to look at this process quantitatively because I find that a quantitative understanding in terms of looking at a mathematical equation gives you a better sense of how to deal with this phenomenon from a qualitative perspective. Okay, let's start off by quickly reviewing an electric motor and the motor effect. In the motor effect, what we had is we had current that was being supplied by a battery, and that current passed through an armature. If you look at this diagram at the bottom, the armature would be this yellow rotating loop. When we take that armature, put some current through it, and put it through a magnetic field, and I believe the magnetic field is produced by the stator. So current in an armature through a stator, which would be these jumbo bar magnets. What that'll do is that'll result in a magnetic deflecting force acting on opposite sides of the armature, and those forces cause the twisting of the armature, which is torque. You generate torque about the actual armature. If you look at this from an energy perspective in terms of what we are doing, we're starting off with current from a battery. Current from a battery is electric energy. And what we're doing is, as a result of the deflecting magnetic force generating torque, we're getting the armature to move. In terms of energy related to motion, that is kinetic energy. So what we're doing is we're taking electrical energy and we're getting mechanical, specifically kinetic energy out of an electric motor. More specifically, it would be rotational kinetic energy. Although we don't have to worry about rotational kinetic energy from a quantitative standpoint in Physics 30. Now, I've identified up here something called symmetry in nature. What symmetry in nature means is the reverse of a certain process true? And here's what I mean. So in the motor effect, I can convert electrical into kinetic energy. The symmetry would be asking, can I go from supplying kinetic energy to getting electrical energy? If I compare this to a motor, it would be saying, if I take a wire, subject it to torque in a magnetic field, can I go backwards and can I get current? And the answer to that is yes. You may have seen at a science center of some kind that there might be like some kind of what do I want to call it, like a apparatus or display. Display is the word I'm looking for, where that if you pedal a bike, you can actually get a light bulb to glow. So what you're doing is you're pedaling the bike, you're making the wheels of the bike rotate. That's rotational kinetic energy, and you're causing a bulb to glow, which means that somehow that kinetic energy is being turned into electrical energy. We call that the generator effect. If you can take motion, kinetic energy, and you can turn it into electrical energy, that is the generator effect. If you look at this in terms of torque and current, this would be the equivalent of taking a wire, exerting torque on it, so a force that causes the wire to twist, put it through a magnetic field, and then you can get current. So the second picture kind of illustrates this. What this picture is trying to show is that you have a person grabbing a wire and physically moving it between two bar magnets, then seeing if you can generate current. This device here would just be an ammeter, so that's not a battery. All an ammeter does is an ammeter can just detect the presence of current. And if you move this wire through a magnetic field, you can get some current. If this wire was maybe connected to a light bulb, perhaps you could get the light bulb to glow. So that's what we're going to look at over the next two lessons in the magnetism unit, this generator effect. We're going to start off by looking at a couple of experiments that demonstrate the generator effect. At this stage, we're not going to explain why the generator effect occurs. We'll just look at two experiments, then we're going to talk about a fundamental law, and then we'll come back and explain the observations from the experiment. The first experiment was one that you would have performed in the classroom, doing one of those mini labs. So I think it was mini lab number 3, where we had a solenoid, and the solenoid, you can see this picture, is connected to a digital multimeter, and the digital multimeter was set to act as an ammeter. And again, all an ammeter does is an ammeter detects the presence of current. And then you were asked to do a bunch of things with the magnet. You were asked to like move it in slower, change the direction in which you're moving it, so pull it out, and to see what effect that had on the different numbers of the ammeter. And here are some things that we should have observed. The only time you can induce current induce current inside of the solenoid is if there is relative motion between both the bar magnet and the solenoid. The easiest way to do this would be if you just kept the solenoid stationary and you move the bar magnet in or the bar magnet out. There would definitely be relative motion between the bar magnet and the solenoid, and you would induce current. However, if you took both of these things, like say you took the bar magnet and I moved the bar magnet down at a velocity of negative 10 meters per second. There's no way you can move that fast, but whatever. And let's say you took the solenoid and you also moved the solenoid down at a velocity of 10 meters per second. Again, not totally realistic. But in this case, because they're moving at the same velocity in the same direction, there's no relative motion. So if you move the solenoid and the bar magnet as a unit, there's no relative motion between them. And in that case, you would actually not induce any current. So there must be relative motion to induce current. 2, the faster you do this, the greater the current that would be induced. So for example, if like you move this at a more realistic number of maybe like 1 meter per second, the motion of the bar magnet, and then you like drastically sped it up to our unrealistic number of 10 meters per second, you would actually generate some more current. And we'll talk about why that happens a bit later. Third observation is that if you move the magnet in the opposite direction, you induce current in a different direction. So for example, let's say that you did move the bar magnet straight down, okay, into the solenoid, and perhaps this caused current to be induced in a direction here. I'm not sure if it would induce it in that direction. We'll deal with what direction the current would be induced later on. And then you reverse the direction of motion. So let's say that you took the bar magnet and now you moved it out. Moving it in the opposite direction would induce current in a different direction. And again, we'll talk about something called Lenz's law, where we can actually predict, well, what is the correct direction of the induced current, depending on whether you move it into the bar magnet or move it into the solenoid or out of the solenoid. So that's experiment 1. Experiment 2 was not one we looked at in class, but I'll just quickly go through it right now. Okay, so in this experiment, you have 2 conducting loops that are side by side. Let's focus on the loop on the right-hand side. So this loop on the right-hand side has a resistor, which is represented by that jagged line. It has a switch, which is currently open, and it passes through a battery. When I close the switch, then you're going to induce current the battery will generate current that would go away from the positive terminal, and it would go into the loop. At the very top of the loop, would be moving in this right direction and then back towards the negative terminal. Beside this one circuit, on the left-hand side, I have a parallel loop, And this parallel loop is just connected to an ammeter. So there is no battery source on the left-hand side. What we notice is that when you open or close that switch, you induce a current very briefly on the left-hand loop. Okay, let me just draw a little graph to kind of like show what this might look like. So I'll call this current on the right loop. So let's say we had a graph of current on the right loop. And we'll just do it as a function of time. When you close the switch, what's going to happen is the electrons in the circuit are going to, when the circuit's broken, they're not moving. So your starting current when the switch is open would be nothing. When you close the switch, those electrons are going to very quickly accelerate to some kind of a constant current. Okay, so this horizontal line right here represents the constant current that the electrons would accelerate to after you close the switch. Now, when you open the switch, you break the circuit, those moving charges would then go back down to rest. Okay, now, we only observe current induced on the left-hand loop during the time when the switch is just open or just closed. So if we take this part of the graph, I'll just highlight it in green. This part of the graph was dealing with when the switch was closed. And in that time span, where the electrons go from not moving to moving at some constant speed, we induce current on this left-hand loop, but only in that time when the current is changing. On this part right here, which is when we open the switch, once again, we induce current. I'll say induce current on left loop. And same thing right here. When we close the switch, we induce current on left loop. When you have a constant current at the very top, no induced current. Now again, at this point, my intention is not to explain why this is true. It's simply just to provide like some observations in terms of when you actually induce current or not. So opening or closing the switch, you briefly induce current on that left-hand loop. The instant the current on the right-hand loop is constant, you no longer induce current on the left-hand loop. We'll come back to this and explain why this happens after addressing something called Faraday's Law. Faraday's Law, named after the scientist Michael Faraday, is a very, very important law in talking about the process of electromagnetic induction. Again, electromagnetic induction is where you're taking motion and you're turning it into electricity. And this is what the law states. If you want to induce current in a conducting object, the way to do that is you need the magnetic flux through a certain area of the conductor to change. So a changing magnetic flux induces current in a conductor. Immediately, you're probably wondering, well, what is magnetic flux? Is it the same thing as magnetic field? They're related, but not quite the exact same thing. So I'll just very quickly explain what magnetic flux is. Magnetic flux. This is a qualitative definition of what magnetic flux is. If you take advanced placement physics or university physics, you would look at a quantitative way of calculating what magnetic flux is. Magnetic flux, qualitatively, is you can visualize it as being the number of magnetic field lines that pass through an enclosed area. So let's say we have two loops of wire. We have loop of wire 1. When I say a loop, I'm just referring to this outer perimeter here. So I have loop of wire 1 and I have loop of wire 2. Both of these wires enclose the same area. What I've shown inside the area is a bunch of magnetic field lines that are directed into the page. On the loop on the left-hand side, you have 9 magnetic field lines passing through that area. On the right-hand side, you have 16 of those magnetic field lines passing through the area. So if I were to ask you, well, which of these loops would have the greater magnetic flux through the area, it would be number 2. Because picture number 2 has more field lines passing through the same enclosed area. Therefore, 2 has a greater magnetic flux than area 1. What Faraday's law tells me is that if you have an enclosed area and you count the number of magnetic field lines through it, if you change the number of magnetic field lines through that area, that is the only time you can induce current. So, for example, if I went from having 9 magnetic field lines to 16, when I have that change in magnetic field lines, that is when I induce current. Or if I started with 16 magnetic field lines through the area and I went in the reverse direction to only having 9 through there, you would also induce current. But it only occurs when the magnetic field is going to change. Now, let's use this to explain those two experiments. So let's go back to the conducting loop one first. Okay, so let's identify what's happening before the switch is open before the switch is closed and after it's been closed. Okay, so let's say this. Let's say before the switch is closed. Before the switch is closed, the current would be equal to 0. If you have no moving charges, then you don't produce any magnetic field. So again, there's 2 sources of a magnetic field. One is you need a ferromagnetic material with aligned domains, and 2, moving charges will produce a magnetic field. So before the switch is closed, there's no current, there's no magnetic field. Now compare this to after the switch is closed. After the switch is closed, you would go to some current. I don't know what the current is. Maybe the current would be something like 10 amps. So there's a change in current. As the current gets bigger and bigger and bigger, the magnetic field changes along with it. So if you have slow moving charges, then the magnetic field produced by each of those individual charges is smaller. If you have faster moving charges, then it produces a larger magnetic field. So after the switch is closed, I would get current, and then I would get a magnetic field that, who knows what the number is, maybe it's like a 2.0 Tesla magnetic field. Each of these moving charges, so for example, if we drew like I know conventional current is supposed to be a movement of protons. Like let's say we had like one of my conventional current charges, a proton. Each moving charge produces a magnetic field. Its magnetic field will change if its speed's changing. So if I use Faraday's law tells me I can only induce current in this left-hand loop if the magnetic flux is changing through an enclosed area. The enclosed area I would consider would be this enclosed area that's enclosed by the loop. So initially, the number of magnetic field lines that come from the right-hand side is nothing. Okay, before the switch is closed, you have no magnetic field being produced. Once you turn the current on, you then go to having some kind of magnetic field. So what you're doing is when you go from a magnetic field of 0 to a magnetic field of 2.0 Teslas, your magnetic flux is changing. Your number of field lines changes. So you go from having no magnetic field lines produced to having, a bunch of magnetic field lines. So you have a change in number of magnetic field lines, which tells me my magnetic flux has changed. Therefore, you induce current. Once you get to the constant current, the charges are just producing the same magnetic field. Like, for example, maybe went from having 0 magnetic field lines to having, again, I'll make these numbers up, say like 15 field lines. Once the current is constant, well, the number of field lines produced would just also be a constant. If the number of field lines through an area is constant, your magnetic flux doesn't change and you do not induce any current. Now, when you break the circuit, you just go in the reverse direction. If you break the circuit, you would go from having 15 magnetic field lines back to having nothing. So once again, you have a change in your magnetic flux because the number of field lines passing through the enclosed area is changing. So that is why we only induce current when briefly after you close or open the switch, because those are the only points in time where the number of field lines passing through this loop on the left-hand side here is changing. And then we would observe current in that ammeter. Let's go back to experiment number 1. Now, I'm going to draw a picture of just the top of the solenoid. Okay, so that's just the top of the solenoid. My enclosed area would just be the cross-sectional area of the solenoid. Now, let's say I told you to just stand at the top of pretend you could actually see magnetic field lines, like you had like some special kind of vision, and I gave you the worst job in the world. I told you just to stand at the top of the solenoid and observe how many field lines pass through that enclosed area. So that's all you got to do. You sit there and you just count how many magnetic field lines pass through the area. Now, let's look at what happens as we move this solenoid close to move the bar magnet close to the solenoid. Okay, so here's my magnet, North Pole, South Pole. I'm going to draw some magnetic field lines from this. I'll just do it in a different color. Let's use green here. Okay, so out of the north, into the south, out of the north, into the south. I'll do some more and I'll really exaggerate these ones. So I'll do like out of the north, loops all the way back around, into the south, out of the north, back into the south. Oops. I drew the field line in the wrong direction through the middle of the solenoid. Sorry about that. Just let me quickly, not the solenoid, the bar magnet. Just let me quickly redraw that guy. Okay, and let's get the correct direction here. Not that the direction of the magnetic field lines is important, but okay, so right now, when this bar magnet is at this location, if I said to you count the number of magnetic field lines that pass through that solenoid, well, I guess if it actually passed through, like you would have like, if I followed along, like out of the north, back into the south, you'd have like 1, 2 loops that pass through. Now, let's say I brought the solenoid closer. So if I brought the solenoid closer, sorry, I keep calling it the solenoid. I bring the bar magnet closer. So let's just draw it over here. Okay, so that's my solenoid. Here's the enclosed area that you're staring at. And let's bring the bar magnet so it's like the pole's like pretty much right on top of the solenoid. Okay, so the magnetic field lines would then be, let's do out of the north. I'm going to exaggerate this a bit. Into the south, out of the north, really big one. Back all the way into the south, out of the north, into the south. We'll do that big one again, out of the north, into the south. Okay, now, if you counted the number of loops that pass through this enclosed area, you would now have this one, 1. You'd have this one, 2. You'd have this big one, 3. And you'd have that smaller one, 4. So as you bring the bar magnet close to the solenoid, you're changing the number of magnetic field lines that pass through that enclosed area. If the number of field lines pass through that enclosed area, then you induce current. Now, if you move them together as a unit, like for example, let's look at the left-hand picture here. And right now I have 1, 2, 3, 4 magnetic field lines passing through. If I move them as a unit so that there's no relative motion between them, I would always have the same number of field lines passing through. If the number of field lines passing through doesn't change, then you don't induce current. So that's why you must have relative motion. If you have relative motion, then the number of field lines passing through that enclosed area is going to vary. And according to Faraday's law, if the number of field lines through an enclosed area changes, then so does the magnetic flux, and that is my condition necessary to induce current. All right, now let's introduce another hand rule I can use to predict, well, what is going to be the direction of induced current in one of these conductors. What you want to do is start off by taking your fingers and you point them in the direction of the external magnetic field. So that's no different compared to our hand rule we used dealing with either a moving charge through a magnetic field or a current carrying wire through a magnetic field. You take your thumb and you point it in the direction that you are physically moving the wire. So for electromagnetic induction, you usually grab an object and you move it. Your thumb points in the direction that you move the object. And then 3, your open palm is going to face the direction of induced current, if it's your right hand, or induced electron flow if we're talking about the left hand. Let's look at an example of this. First thing first, I'm going to clarify a Cartesian grid. So we'll say that they've already got the grid drawn in the picture here. We'll call this the y-axis, we'll call this the x-axis, and we'll call this the z-axis. So I have a couple of bar magnets. between these bar magnets, there'd be a magnetic field that goes out of the north and into the south. We'll just draw one magnetic field line. I have this loop of wire, and what I'm going to do is I'm going to grab that loop of wire and I'm going to move the whole thing straight up. So we're moving the whole thing up in this Y direction. And I want to figure out, well, as a result of moving this thing, what direction would I induce current? Okay, well, let's identify how we do this. Okay, so it does say electron flow in the picture, so we'll use the left-hand rule. I'll do it over here. So I'll say left hand, because we're dealing with electron flow. B represents the direction your fingers would point. So your fingers, if you look at how it's drawn right here, the magnetic field is pointing from north to south. That is in the positive X direction. Your thumb is going to be the direction that you physically are going to pull up the conductor. So in this case, I'm grabbing the left hand of the wire and I'm pulling it vertically up in that Y direction. So I move that up in the positive Y direction. The direction of induced current, I, is going to be the direction that your open palm is going to face. So the way I would do this is take your left hand, make sure your thumb and fingers are perpendicular to each other. I would take my fingers and point them in the positive X direction, which would be towards the right. Then I'd rotate my wrist so that my thumb is pointing upward from my perspective, and your fingers are pointing towards the right. And if you do this correctly, your open palm should be facing at you, okay, with your left hand. So facing at you would be in the positive Z direction. So this electron, I mean, there, by the way, like in an actual circuit, you'd have like tons of electrons just stacked side by side by side. If we look at this one electron in the magnetic field here, that the direction of induced electron flow, E negative, would be in the positive Z direction. So what that does is it's kind of like a domino effect that once this guy starts moving in the positive Z direction, whichever electron's in front of it is going to get bumped over. It's going to get bumped over. They keep getting bumped over until what you get is the direction of electron flow from a top view perspective here, I believe would be counterclockwise. So qualitatively, that's how we deal with electromagnetic induction. So we know the law that tells us when electromagnetic induction occurs. That's Michael Faraday's law. And we also have this modified third-hand rule, which can allow us to predict what is the direction of induced current or electron flow. Now, as mentioned at the start of the lesson, I know that it says in the program of studies only to do a qualitative explanation of induction. However, I find it's more helpful if you can see a mathematical equation, because the mathematical equation will also help you identify when induction occurs. Now, when you induce current in a wire, you also induce voltage in a wire. There's a quick way to justify this. We know Ohm's law tells me that delta V is equal to I times R. So if we're looking at a conducting wire that has a certain amount of resistance in it, and we induce current in it, we're also going to induce voltage in that wire. Oftentimes, the induced voltage is referred to as an electromotive force. I said force in quotation marks because it's not really a force. Like, it's not a force in the sense of like some kind of external outside force is pushing at my electrons, getting them to move. The external force, I mean, the force that gets them to move is a result of the process of electromagnetic induction. So it's not really a force, but the term EMF is kind of just stuck around in being used interchangeably for identifying induced voltage. To calculate the voltage induced in a conductor, we can use this equation. Delta V is equal to the magnitude of the vector L times the magnitude of the vector V times the magnitude of the vector B times sine theta. In this equation, L represents the length of the conductor in the magnetic field. V represents the speed of the conductor. B represents the magnetic field intensity. And theta can be an angle between one of the following two variables. It can be the angle between V and B or L and B. If I wanted to figure out how much current is induced in the wire, mathematically, I could simply just manipulate Ohm's law. So Ohm's law tells me delta V is I times R. To manipulate for I, divide both sides of the equation by R, and you get your induced current is delta V over R. Now, I just want to look at this equation here. So if I said, like what could I do to maximize induced current? Like obviously, when you're doing electromagnetic induction, you probably want to get your maximum output in terms of current. So the equation's helpful because it can tell us all the different things we can do to maximize our induced voltage. If we maximize our induced voltage, we'd maximize the current because there's a direct relationship between them. So the first thing is that you'd want as much wire as possible you can get in the magnetic field. The faster you move the wire, the more current you should induce. Let's talk about that one for a quick second. So faster motion leads to bigger current. If you have faster motion, it means that you're inputting more kinetic energy. If you input more kinetic energy, I would expect to get more electrical energy out of it. Think of this in terms of like conservation of energy. The more energy you put into the system, the more energy you're going to get out of it. So if I move the conductor faster through the magnetic field, I put in more kinetic energy, and that results in me getting more electric potential energy out of it, which results in a larger current. We'll talk more about the consequences of conservation of energy in the next lesson. How else could I make the induced current bigger? Well, just use a stronger magnetic field. And the other part is theta. So what theta represents is it's the angle between the length of your conductor and the magnetic field, or between the magnetic field and the direction you're actually moving the conductor. Sine of theta is a maximum when theta is 90 degrees. So what you want is you want everything to be perpendicular. If we go back to this previous picture, this is the case. If you look at the diagram, the direction of the magnetic field is towards the positive x direction. The direction of the velocity of the conductor is in the positive y direction. Well, that's a 90 degree angle. So you got a 90 degree angle between the vectors v and the vector b and the vector b. You also want to have a 90 degree angle between the length of your conductor and the magnetic field. So the length of my conductor would be in this direction. That's along the z-axis. The z-axis is also perpendicular to the direction of the magnetic field. So this would be perfect in terms of maximizing your induced current because everything is perpendicular to the magnetic field. The other thing to consider in the equation is when would you not induce any current? Okay, we'll look at the equation. So first of all, if you didn't have any wire, no length of wire in the magnetic field, then obviously you're not going to induce any current. Secondly, if the wire is just sitting there and not doing anything, you're not going to induce any current. Third thing, if you have no magnetic field, there's no chance of inducing current. The other one is about the angle theta. If theta is 0 degrees, you would also induce no current. So what would that mean if we go back to this picture? Okay, this picture's starting to get a bit cluttered, so maybe I could just erase this. Okay, so there's a couple things you could do that would result in you getting no induced current. If I took this conductor and I moved it in the same direction of the magnetic field, so in this case right here, the angle theta between V and B is 0, so the direction of motion is parallel to the magnetic field, you don't induce any current. So that's one possible scenario. The other possible scenario is if you have the length of the conductor the length of the conductor parallel to the magnetic field. So that would be like if you have the conductor lined up like this. In this case, the length of the conductor, L, is also parallel to the magnetic field, and you would induce no current in that conductor. So like I said, I find it more helpful just seeing the equation for induced voltage or current to develop a better understanding of when you can or cannot induce voltage or current in a conductor. All right, so a couple of examples to finish off the example booklet. So it says, identify the direction of induced current for the actions taken in each of the diagrams shown below. Okay, first of all, let's clarify what we see here. So in part A, what I have is I have a resistor, and this resistor is part of a broken circuit. The reason I say broken is because there's no wire that connects this right end here at the top to the right end here at the bottom. Okay, it's broken. What we're doing is we are taking a conducting rod and we're putting this rod on top of the circuit and we're kind of like rolling it. We're just rolling it along the top of the circuit and we're rolling it towards the right. What I want to do is figure out, okay, what is the direction of induced current in this circuit? Now, maybe before talking about the direction of the induced current, maybe we should just take a step back and identify why do you induce current in the first place? So, inducing current, according to Faraday's law, tells me that if you have a changing magnetic flux, you will induce current in a conductor. Okay, so specifically, we're looking at the changing magnetic flux through an enclosed area. So currently, right now, what's the area enclosed by the loop? Well, it would be this area. The moving rod encloses the area. Right here, the number of magnetic field lines passing through that enclosed area would be 8 of them. Now, consider some time later, when the rod's over here, I believe at this point, you would then have, so let's just kind of like sketch this enclosed area now. So I'll use a different color. The enclosed area would be a lot bigger. So the enclosed area would now be this big area. This big area would have now 16 magnetic field lines. So what you've done is, as a result of moving this rod along the actual moving the rod along the broken circuit, you're increasing the number of magnetic field lines within that area. If the number of magnetic field lines within an enclosed area is changing, then your magnetic flux changes, and then you're going to induce current. I realize that the enclosed area is changing, but I don't want to say there is a direct relationship between the number of field lines that are being enclosed and between the enclosed area itself. We'll just safely assume that as you're increasing the area, maybe like the ratio of area to field lines is also changing as well. So you are inducing a current. Okay, let's get rid of all this because it's just too much to look at. Okay, all we need to do here is apply the modified third-hand rule to figure out the direction of current. So here's how I do it. First things first, we're dealing with induced current. So induced current is going to be, in both scenarios, we're going to use our right hand. So for this one, start off with your fingers. Magnetic field is your fingers. Your magnetic field is being represented by your fingers, and that is being directed out of the page. The moving conductor is this rod, and what you're doing is you're like taking your hand, grabbing it, and you're just pulling it along the top of this broken circuit. So that would be your thumb. So we're moving it towards the right side of the page. Your open palm is going to tell me the direction of induced current. Okay, so let's apply the modified third-hand rule. So take your right hand, make sure your fingers and thumb are perpendicular. Take your fingers and point them at you. And you're going to have to, this is awkward. You're going to have to take your fingers pointing at you. You're going to have to rotate your wrist. Your thumb is pointing towards the right. And if you do this, your palm should be facing towards the bottom of the computer screen. So we'll call that the bottom of the page. Okay, now if we go back to this picture, the question would be, well, where do I draw this? Like, where does the induced current start from? Like, do you draw the induced current starting from here? Or do you draw the induced current starting from this side of the wire? Do you draw it on the left-hand side of the wire or on this rod here? Well, the spot where you're going to induce current is going to be on the spot where you actually have a moving conductor. So this broken circuit here is not moving. The broken circuit is stationary. What's moving is the rod. So what I would do is the rod is moving. That's where I'm going to induce the current. So the direction of induced current would be towards the bottom of the page, starting at the rod. Now, if we follow the direction of induced current, so it would then go down here. Now you get to this junction here where you're like, okay, well, what direction does the induced current go? Well, I suppose some of it could get pushed towards the right-hand side, but it's a dead end. So if you go towards the right-hand side, then you're not going to get continuous current. So what we're interested in looking for is like what direction is going to lead to continuous current. Therefore, at this branch, the direction of induced current should go towards the left. And then it goes up through this resistor. And then it goes right through the top part of the branch. And you get back to this junction here. And then to complete the circuit, you would just go back into that conducting rod. So if I drew the direction of induced current, the direction of induced current would be like this. From our perspective, we could then say that I is clockwise through that circuit. And that's my answer to that question. I would be clockwise. The second example is we're taking the entire circuit and we're moving it through a magnetic field. Now, going back to Faraday's law. So why do you induce current in the first place? So Faraday's law would tell me a changing magnetic flux will induce current. Let's look at the number of field lines through this enclosed area right now. So right now, the enclosed area, I would have 3 times 4 magnetic field lines through there. So I'd have 12 magnetic field lines that are enclosed. Now, sometime later, the circuit is going to be located. So it's now, because we're moving it towards the right, the circuit is going to look like this. Okay, now it's towards the right. How many magnetic field lines are in here now? Well, it's 4 by 4, so you have 16. So what's happened? We kept the area constant, and by moving it from left to right, I changed the number of magnetic field lines from 12 to 16. Well, the magnetic flux has changed because the number of field lines has changed, and therefore you're going to induce current. Okay, let's figure out how to use the hand rule here to determine the direction of induced current. Okay, so once again, it's the right hand because we're dealing with induced current. Magnetic field, which is your fingers, still points out of the page. The direction that the entire wire is moving, V, which is represented by your thumbs. Again, that's your input here. Your input is you're grabbing the entire circuit and you're pulling it. So that's towards the right side of the page. And then we want to know the direction of our induced current because we're dealing with our right hand. That's going to be the direction our palm faces. And once again, the hand rule applies just like it did in part A, so I'm not going to go over the steps of how to do that. It would also be towards the bottom of the page. Bottom of page. Okay, now, once again, you have to ask yourself, well, where is the current going to start off in? Is it going to start off in this part of the wire going down? Or is it going to start off in this part of the wire going down? It's definitely not going to be the top, because if you had current at the top of the wire, current being induced down, it wouldn't go anywhere. Same thing at the bottom of the wire. The current is not going to start at the bottom of the wire because it has nowhere to go. So let's get rid of that. So we're down to this one. Is current going to be induced on the left-hand side or the right-hand side? Well, current is only induced if you are in a magnetic field. The part of the wire that's in the magnetic field is the right-hand side. The left-hand side is not in the magnetic field. So you actually don't start off by inducing current on that side. So let's get rid of that. Therefore, if we draw it, so current gets induced in the magnetic field. So that'd be directed downward. Then it would go towards the left, then up, then right. And then once again, if I look at the direction of induced current in that circuit, I would also be clockwise. All right, so that's an introduction to electromagnetic induction. I realized that was quite a bit of stuff to go through because we had to look at it both qualitatively and quantitatively and look at a hand rule we can use to predict the direction of induced current. So there's an assignment called electromagnetic induction. You can complete it if you would like some practice with these problems. And then in the next lesson, we'll talk about Lenz's law, which will actually conclude the unit on magnetic forces and fields.